Max Planck Institute and Stony Brook. After that, he was professor at Kanazawa University from 1988 to 2018. After the retirement of Kanazawa University at 2018, he is visiting professor at Toyama University. He is doing theoretical investigation in high energy physics and cosmology. Today, he is going to talk about the spontaneous generation of masses and hierarchy problem. Professor Kubo, please start. Thank you very much.
Oh, yes. Thank you very much for a nice introduction. Yes. Also, I thank you and especially Hyun-Min for the invitation to the seminar. I am very pleased. Yes, I studied in Germany, and as you said, I retired 2018. And since then, I am staying in Germany for half year and the other half year in Japan. Okay. So, yes, as you see, this is my the title of my talk. I wrote hierarchy problem very small because I do not feel very confident to talk about this problem because this problem is so difficult problem, and in fact, I'm not suggesting any solution to this problem. Okay. Now, most of the work has been done together with a group of Heidelberg, Max Planck Institute, and also with a colleague of Kanazawa University. Yes, Toyama University, there are some problems, but after the talk, maybe I can tell you why I'm in Toyama University. Okay. Now, to the next page. Okay. Hierarchy problem is, as I told you, is a very, very difficult problem. It is a problem because there are so much different energy scales, and we do not know why. Right? And related, and the more technical problem is the naturalness problem. And it is a problem because it is a priori not clear whether it is possible to realize such different energy scales without any fine-tuning of parameters. I show you this article by Wilczek that appeared in Physics Today 1999 and 2000. It is about Wheeler's phrase, mass without mass. He used this phrase, mass without mass, to explain his wish to remove all dimensional parameters from the fundamental equation. It's clear if we start with a theory containing the mass terms from the beginning, we have no chance to explain the origin. So this led me to the idea to extend the standard model and also Einstein's theory of gravity in a scale invariant manner. Okay. So these are the fundamental scales, as we know, and I ask myself about their origin. That is, I am shifting the question of why these ratios of parameters, dimensional parameters, are so small, to the question of where they come from. So the second problem is easier to solve, and I hope, or it may be hoped, that after we have solved the second problem, maybe there is a route to a solution, to the solution of the first original hierarchy problem. Now, you may say the scale invariance is broken by anomaly. So at the quantum level, there is a scale anyway from the beginning. This is true. However, scale anomaly cannot directly generate mass gap. So to generate a mass gap, scale invariance has to be spontaneously broken. And 1973, Coleman Wenberg considered the standard model without Higgs mass term. So in the limit that the Higgs mass term goes to 0, they found the electroweak gauge symmetry can be spontaneously broken through radiative correction. Unfortunately, the resulting Higgs mass is 10 GeV, so it is too small. Also, if you do not assume that the top quark mass is small, so if you include the top quark mass, the electroweak gauge symmetry cannot be radiatively broken. And I would like to remind you that the Nambu and the Nambu and Yoshino in early 60s already considered the dynamical symmetry breaking. And just after that, the Goldstone translated the idea of chiral symmetry breaking into the language of the potential, which I used here. So in the language of the potential, it is much easier to understand the symmetry breaking, right? Now, there was also old discussion about how to generate Planck mass radiatively. And this is a partial old list of papers, and this is of course not complete, but also I'm not going to discuss these papers in detail, but I will come back to this issue later on in my talk. There are indications for scale invariance. So probably you might have seen this graph many times. And this graph shows that Higgs quartic coupling at the Planck scale, and depending on the Higgs mass and the top mass. This graph, I took this graph by this paper, colleague in Heidelberg, and so this green band shows, for instance, that Higgs quartic coupling at the Planck scale vanishes, and so on. And here is a critical point. So what this graph shows is that the standard model remains perturbative all the way to the Planck scale. Do you hear me, right? Well,
yes.
Okay.
Okay.
Okay, very good. So this is the renormalization group running of the Higgs quartic coupling. You see here desert. This desert means that the scale invariance is broken only by anomaly all the way to the Planck scale, except for the soft breaking by the Higgs mass term itself. This kind of the behavior was already predicted by Lindner in 1968, and this is a graph that you have seen also many times. Around the same time in Munich, we have considered the standard model couplings in different but somehow related contexts. Namely, the standard model with all the couplings vanish, except the Higgs coupling, Higgs quartic coupling, top Yukawa, and the QCD coupling. The standard model becomes asymptotically free, completely asymptotically free. Then we found there is a maximal value of the ratio of the Yukawa coupling squared divided by Higgs quartic coupling, which can be translated into the mass ratio of the top and Higgs. It becomes 1.9, which is very close to the experimental value. So that was the indication for the scale invariance in the standard model. So at low end, let's say low energy. There are also scale invariance at high energy. So as you have seen this picture, this is the experimental constraint by Planck and Bisect on the so-called tensor to scalar ratio and the scalar index in the CMB. It is quite often said that the scalar index, scalar index, that the fact that it is very close to 1, it indicates a scale invariance. And this is true only for power spectrum. However, if you look at only the NS, the scalar index, there are many models that are consistent with this, but these models are not scale invariant. On the other hand, if you look at the tensor to scalar ratio, which is very small, this is predicted by R-square inflation. As you know, the R-square inflation is approximately scaling value. So it is this tensor to scalar ratio, this smallness of the tensor to scalar ratio is indicating the underlying scaling variance. So let's look at more in detail. So this is a Lagrangian for the R-square inflation. And also, you know that the Higgs inflation also predicts the same value. So the first one is Lagrangian for the R-square inflation. The second is Higgs inflation. And the first term is the Einstein-Hilbert term. So the Einstein-Hilbert term obviously breaks scaling variance. However, this second term are scaling variant because curvature tensor has a dimension 2, and also Higgs field has a dimension 2. Now, this is a Lagrangian in the Jordan frame. And the so-called slower picture is given in the Einstein frame. So you go from the from the Jordan frame to the Einstein frame. Now, in the Higgs inflation case, Higgs is inflaton. In the case of the R-square inflation, there is a scalar which is involved in R-square, which is a higher derivative. And if you go to the Einstein frame, you have this inflaton, and you can write down the potential, the function of the inflaton. Then the potential looks like this. Now you see, for a large inflaton value, the potential becomes very, very flat. This flatness comes because this scaling invariant part dominates the Einstein term. So if the scaling invariant part dominates, you get the super flat potential. And to remember that the tensor to scalar ratio is the square of the gradient of the potential. That means in the scaling invariant theory, the R square tensor to scalar ratio becomes automatically very, very small. So this is an indication for the scaling invariance. Now I come to how to, let's say, break scaling invariance, or how to generate scales. There's obviously perturbative scenario, which I mentioned already. This is the Coleman Wenberg scenario. There's also non-perturbative scenario. Here, one uses strong interactions and non-abelian gauge theory. And due to the strong interaction, fermion bilinear can form, or bosonic bilinear can also form. These condensation can be used to generate scale. Scale invariance can be also broken by boundary condition, which is used by these people to discuss inflation. This is a very interesting paper. If you look at the, if you're interested in, you can look at this paper. But there is also possibility to relate wide gauge freedom to scale symmetry breaking, which was advocated by Hyun-Min and also his collaborators. But in my talk, I am considering only first two possibilities, so perturbative scenario and non-perturbative scenario. As I told you, original Coleman Wenberg idea does not work because of we have a very heavy Higgs. And so this model has to be extended. This has been done by many people, and there was a lot of activity in the last years. And also it started already 2007. It's already 15 years old. And also there is a non-perturbative scenario. The original non-perturbative scenario was used in so-called technical model. But in the technical model, there was no scalar. And fermions, so the called the fermions, they had non-vanishing standard model quantum numbers, and that leads to flavor changing neutral current problem, as you know. Now, this Korean group, including Ko-san, they constructed the hidden, let's say, QCD model And in the heating sector, a robust energy scale was created by chiral symmetry breaking as in QCD, and it was transmitted by a standard model singlet scalar. And since the scalar is a standard model singlet, the forever changing neutral current problem was avoided. And after that, there are many similar models, and we have also considered a very similar model. And there are nice review by these people and also references. And Jung, Lee, Namsan, they had a very huge references, huge list of the references. And Vetteri and Salvino, they had a nice review. If you're interested in, you can look at these reviews. And since there are so many models, but I would like to talk about one very specific model to see how naturalness appears in the scale invariant extension of the model. Okay. The Higgs naturalness problem was due to the quadratic divergence. This is a quadratic divergence diagram. That means the neutrino and heavy neutrino contribute to the mass correction of the Higgs. So it was known that this correction becomes very large if the right-handed neutrino mass is very large. And Brivo and Trott used this correction to trigger electroweak symmetry breaking. So if you like to trigger the electroweak symmetry breaking and also explain the smallness of the active left-handed neutrino, it turns out the right-handed neutrino mass is about 10 to 7 GeV. Now, original model was not scale invariant, but it is now obvious to extend this model in a scale invariant way. This is done by these people. So originally you had the quadratic divergence, but this is replaced by a logarithmic correction. This is a correction to the Higgs-Portal coupling. Now, if S acquires a web, you can see that it produced the Higgs mass term. Okay, and from that correction, you can compute the Higgs mass term, and this is like this. So this is the logarithmic correction to the Higgs-Portal coupling. Therefore, what happens is that the Higgs naturalness is converted to the naturalness of Higgs-Portal coupling. It turns out, as you see, that this Higgs-Portal coupling has to be very, very small for the Newton option to work. So let's look at more in detail. These are the beta functions for Higgs-Portal coupling. In this model, there are two scalars, two standard model Higgs scalars. Therefore, there are two Higgs-Portal coupling. It's called S and R. And there are the two symmetry, S get web and R does not get web. So the original problem is lambda HS. Now, most of the terms in the beta function are proportional to lambda HS. However, there is a term which is not proportional to lambda HS. This is this correction. It comes from the same diagram, one loop diagram, right? So what is assumed in the neutrino option is that the radiative correction, this is a radiative correction, is much larger than lambda HS itself. If lambda HS is very large, we cannot say anything. There is no prediction. So if we assume lambda HS is very, very small, so this small, then since we know the Yukawa couplings, then we can say something about that, right? So for this mechanism to work, the lambda HS has to be very, very small. Now, so this is the origin of the naturalness. However, it is nevertheless natural because in the limit that lambda HS, lambda HS is 0 and lambda HR is 0, and also one of the Yukawa coupling is 0, there is no correction. So if they are 0, they remain 0. In this sense, it is natural. So what happens here is, in this case, there is no cancellation like big minus big is small. So there is no cancellation of the huge quantity against huge quantity. However, you can get very small number by multiplying a small number with a big number. So this is how you get a small number in this case. And therefore, the naturalness problem for the dimensionless coupling is somehow softer. Okay. Now, if you include the gravity, you will see the situation change a little. Now, here I assume that the Planck scale is spontaneously generated, which means I generate also Einstein-Hilbert term spontaneously. The most economic way and simple way, this was also advocated many years ago, is like this. So you have a non-minimal coupling, so you have a scalar S and coupled to the curvature. And the curvature has a dimension 2, this is a dimension 4 operator, so that the coupling XCS is a dimension. If S acquires VEP, then you create Einstein-Hilbert term. And therefore, the Planck scale is the VEP times square root of this coupling. This idea was used recently also by many people. This is a partial list of the reference. Now, you will see that the spontaneous generation of the Planck scale and also the desert makes a relation between and make it possible the direct relation between the standard model and the Planck scale of physics if the quantum gravity is known. But as you know, the quantum gravity is not known, although there are various ideas. So I picked up 3 different ideas. One is based on non-perturbative physics. This is a non-perturbative scenario. So if you assume there is a fixed point and the theory is safe, it's called asymptotic safety. And it's studied a lot, especially in Heidelberg. There's also perturbative scenario. Perturbative scenario is very old, studied by Wertmann, for instance, and also until now there are continuous progress. There are, of course, completely different scenario like strings, for which I have no reference here. But here, let me discuss a perturbative scenario. Okay? The perturbative scenario is based on the denormalizability of quadratic gravity, which is proven already 77. The quadratic, what is the quadratic gravity? Yes, quadratic gravity includes R square, this is the scale invariant term, and also Y tensor square is also dimension 2, so kappa is dimensionless, and also non-minimal coupling. So, but there is no Einstein term because Einstein term breaks scale invariance. So quadratic gravity consists basically these 3 terms, and also kinetic term for the scale. And this theory is denormalizable. This is because these 2 terms, especially Y tensor square terms, act as a kind of regulator, and which makes the high energy behavior of the theory much milder than an Einstein. So therefore, it becomes denormalizable. Since it is denormalizable, we can control the quantum correction, also quantum correction to the standard model. However, there is a big problem in this theory. This is called the massive spin 2 ghost problem. And massive spin ghost problem is present because R square and especially Y tensor square contains 4 derivatives instead of the 2. So this is a higher derivative theory. And in general, higher derivative theory contains. I'm not going to discuss this difficult problem in detail. However, I would like to illustrate this problem by using a very simple, oversimplified mechanical system. Okay. Sorry. So this is a mechanical system, and the problem is very, very old, 170 years old. This is much older than quantum mechanics, much older than gravity. So this is a mechanical problem. You see here, this is a Lagrangian for the mechanical problem, and the x is a coordinate, x dot is a kinetic term. However, I have x2 dot square here, right? X2 dot square means it contains a 4 derivative, and this is the higher derivative theory. Now, it is possible to transform this higher derivative theory in a theory which contains only 2 derivatives. Now, this can be done by using x2. So this is a Lagrangian containing x and x2, where x2 is auxiliary field or auxiliary variables. And using the equation motion, and you insert this equation motion into this action, you get back the original action. So this, at least the second action is at least at the classical level equivalent to the original action. But this second theory contains only 2 derivatives. So since it contains only 2 derivatives, you can apply Hamiltonian mechanism, all these things, right? Which I do. Further redefinition, so I go to x instead of from x1, you get this Lagrangian, okay? Now, x1 is here, x2 is here, and if you look at the sign of the kinetic term and the sign of the mass term, then you see the sign is wrong. So x1 as a positive sign, x2 the minus, so this is wrong sign. Also, this mass term, this harmonic oscillator term is wrong sign. And this wrong sign also appears in the equation of motion. Okay? This is the ordinary equation of motion. However, here you get plus. And if you switch off the potential, for instance, you see that the x1 is a free particle, healthy free particle, and this corresponds massless graviton. And x2, which without potential, it's a normal harmonic oscillator, but because of the minus sign, it's a ghost harmonic oscillator. It corresponds to massive spin 2 particle. And this wrong sign also appears in Hamiltonian, okay? For the healthy particle, I have a plus. For the ghost particle, I have a minus here, and also here minus with the potential. But you can imagine this harmonic oscillator part, this is a mass term, this is a restoring force. If the restoring force for the ghost particle is stronger than the potential, the motion is stable, right? So you can have a stable motion, but I would say that even if the motion is stable, this model is somehow pathological. Of course, this program is called Postography's instability, but not only the instability is the problem. Even if the motion is stable, it is a problem. So for this, I consider a scattering of x1. This is a healthy particle, and x2. The x2 is coming from the left, and the ghost harmonic oscillator is sitting at the origin. So I consider the scattering of 2 particles, right? Now, so upper panel is the trajectory of the healthy particle. So if I click, you see here. It comes from the left and scattered at the origin, and after the scattering, it makes a uniform motion, okay, going out. Okay. Now the lower panel is a trajectory of the ghost particle. Okay. it is sitting at the origin before the collision, and after the collision, it is excited and make harmonic oscillator motion. Okay, it is a stable motion. So if you look at this motion, there is no problem, right? It looks as if everything is okay. Now, however, if you look at the energy of the graviton is a heresy incoming x1. So I start from the left, and if the potential energy is very small, then the incoming kinetic energy is almost the total energy. Then I look at the energy of the heresy particle after the collision. Then you find that the energy of the outgoing heresy particle is larger than the total energy. This is very strange. Since the potential does not depend on the time, the total energy is conserved. You can also numerically see. However, if you see the energy conservation from the particle 1, energy conservation looks very strange. The outgoing energy is bigger than the incoming energy, I mean total energy. So this is the situation. Yes, yes.
In this case, what is the definition of energy? The usual
Energy definition. Yes,
because
since I have Hamiltonian.
Okay, you showed it here.
Yes.
Okay.
Yes, this is the energy. Yes,
Hmm.
yes, yes. If you have a fourth derivative, then it is very difficult to define energy, right? But here I have second derivative. I can have a Hamiltonian formula, and I define as usual, right? Now, this was a classical situation, so I can go to the quantum level. So this is the commutation relation at the interacting level, but I can define the annihilation and creation operators if I switch off the potential, which I do. So this is asymptotic field, which means I switched off the potential. Sorry. Then first of all, you find the wrong sign for the commutation relation, A and A dagger. Usually you have plus sign. And also you find the wrong sign for the Hamiltonian. Okay? You also find that the quantization procedure is not unique. There are actually two possibilities to define a vacuum. You can use A to define the vacuum, or you can use A dagger to define the vacuum. These two systems are different. If you use A to define the vacuum, which is a usual case, you find that the norm of the state are not always positive definite. So you have negative norm state. However, the energy eigenvalues are always positive in this case. On the other hand, if you define the vacuum by A dagger, then you find that the norm is always positive, but energy is negative. So this corresponds to the case of the classical situation. So this has no classical analogy. Right? So there are two ways to define the quantum mechanical system. But this difference also appears if you look at the propagator. This is the propagator. First of all, the overall sign is different from the usual propagator, and also sign in front of the epsilon. Now, this front of the epsilon is very important in many places. However, in quantum field theory, it is important to prove universability. In fact, this plus I epsilon is chosen by Stelle to prove the universability. Why this is important? Yes, there is an intuitive picture why this sign is important. So if you remember that the Weinberg's theorem on power counting, okay? Weinberg's theorem on power counting. This is a theorem for Euclidean momentum. to apply the theorem, we have to go from the Minkowski momenta to the Euclidean momenta. To do this, we have to rotate. Okay? If you have a plus epsilon, all the propagators are plus epsilon, you rotate the energy component 90 degrees on the complex energy plane counterclockwise in this way, counterclockwise. Then you rotate the energy component without crossing a pole. It is plus epsilon defines where the pole is. If you rotate in this way, there's no crossing. Then after that, you can come back to the Minkowski space. So if there's no crossing over the pole, you can apply directly the Wenberg theorem, and then you can, yes. However, if you have a mix, because usually we have mixed sign, right? You have ghost and the normal particles. If you have a wrong sign, you cross the pole. If you cross the pole, you cannot apply the Wenberg theorem. So this is the problem. So this is a universability. However, there is a still unitarity problem because of this indefinite metric, I mean negative norm metric. So I'm not going to discuss further, but if you look at the papers, there are many interesting development in this problem, and this problem is still ongoing. Okay. I'm also very much interested in the problem. This is a very mathematical, also theoretical problem. Okay. Now, I come back to the naturalist problem now. So as I told you, to generate the Einstein-Hilbert term, I use this minimal coupling, then S get the web, and then I have this relation. Now, since S is usually the standard model singlet, it has always Higgs-Porter coupling like this, right? The coupling constant I called it lambda HS. So now S generate Planck scale, the web of S is very huge. On the other hand, lambda HS times the web square has to be smaller than the Higgs mass. This gives a strong constraint, namely lambda HS over CS, psi is a non-minimal coupling, has to be very, very small. Okay. Nevertheless, it could be natural, because I told you natural smallness can be achieved by multiplying a small number with multiplying a big number with a small number, and so on. And the renormalizability, because I am assuming the renormalizability of the quadratic gravity and also scale invariance may provide a solution, or it may be possible to keep the naturalness. But this is not automatic, as you say. Now, to see this a little bit more concrete, I look at the beta function once again, beta function for Porter coupling. And the kappa gamma C are coupling constant to remember the kappa is a coupling constant for y tensor squared, and gamma is R squared, and psi is a non-minimal coupling. Later, maybe I use beta, but psi and beta are the same. And this is a beta function calculated by Savino. And for the individual coupling, there are also references here. And if mu, or the energy, goes to infinity, kappa inverse goes to 0. This is kind of asymptotic freedom. It was found already 82. And gamma inverse goes to infinity, right? If mu goes to infinity. And C's minimal coupling goes to -1/6. Then if you look at lambda HS, where it has go, then we do not know, because the kappa inverse goes to 0, so this is nice. However, here, gamma inverse goes to infinity, and 1 + 1/6h goes to 0. So it becomes infinity times 0, which we don't know within the perturbation. However, if you look at this beta function, you can imagine what is the quantum correction coming from the gravity around the Planck scale. So let's assume the quantum correction around the Planck scale should satisfy this. Then this is a constraint for the quantum correction. So this gives a strong constraint on Xi and gamma kappa because it depends on the Xi and gamma kappa. Once again, if you assume that the non-minimal coupling for scalar is much larger than 1, usually you need it for inflation, and non-minimal coupling for Higgs is smaller than 1, this parenthesis reduced to this, okay? So this number has to be smaller than 10 to minus 33, which is a very small number. So here you have Higgs Portal coupling. Now, there's also beta function for the Higgs Portal coupling, and this side is basically the correction coming from the standard model. You see this correction coming from the standard model is not small. You know, the top coupling is about order 1, so the correction is at most 10 to minus 2. If you insert 10 to minus 2 here, then you find, because of the plus sign here and the CS is plus, the kappa has to be larger than 10 to 15, and also gamma over C square root has to be more than 10 to, larger than 10 to 14. It's a very huge constraint. This is the constraint to satisfy, to make the correction to the Higgs Portal coupling small. Okay. However, you remember I assumed that the scalar coupling, scalar nominal coupling is larger than 1, and Higgs Portal is smaller than 1. But if you do not assume you get this back, then if you assume that the 6 time, for instance, Higgs minimal coupling is smaller than -1, you get minus sign, so you get some, you can have some cancellation. Cancellation means fine tuning. So using this fine tuning, you can achieve that the correction to the Higgs Portal coupling can be made very small, but you need a fine tuning. Now, as I told you, that the Higgs, not only Higgs and the scalar nominal coupling, also coupling for R square and coupling for right tensor square, they contribute to the naturalness of the Higgs Portal coupling. And at the same time, they control the throttle parameters. For instance, gamma is important for the R square inflation of Robinsky, and the Xi and Xs are Higgs or Higgs-like inflation, very important parameter. And kappa also influence, we know the kappa influences tensor to scalar ratio. And recently we find also that this Y-squared tensor term can contribute scale symmetry breaking. I will come back to this model. We have a model based on this. So let me look at a concrete model, how whether these constraints are satisfied or not. Now, this is a model I considered with my colleague in Heidelberg, and this model generates Planck scale and the Dagmara scale, and also right-hand neutrino and electroweak scale from the same mechanism. So they have the same origin. Okay? I have only one origin to generate the scale. So it consists 1, 2, 3, 4 Lagrangian. And the first part is responsible for Coleman Wenberg. And actually I use Gildner-Weinberg mechanism. That means that the coupling constants are so chosen that only S gets wrapped. And actually I assume Z2 parity, which means the sigma does not get wrapped, and Z2 is unbroken. The second one is the gravity parts. I have a non-minimal coupling and R square and Y tensor square. And the fourth one is standard model with Higgs mass term set 0. And I have this dangerous Portal coupling. And I have a neutrino part. And this part is chosen so that neutrino option works. And also I have chi. This is additional Majorana fermion. with Z2 odd, so it is a dark matter condition. Here in this Lagrangian, I use beta instead of the C, so do not, beta is not a beta function in this case. So once again, VEP S generate everything, Planck mass, neutrino mass, and so on. And the sigma VEP is 0. Second Lagrangian generate the Planck mass. And the fourth one, this is the Potter coupling. This is the naturalness, origin of the naturalness. And the last one generates the right-angle neutrino mass, and which is responsible for the neutrino option. And sigma and chi are dark matter conditions. Now, I'm not going to discuss all the details. However, I discussed just the inflation part, so gravitational part. As I told you, in the case of, because of this R square, because R square is a higher derivative, there is an additional gravitational degrees of freedom. This is a scalar degrees of freedom, which is called scalar. And in this model, we switched off the Weyl tensor square term. Therefore, there is, in this model, there is no, at the classical level, there is no spin 2 ghost, but we have scalar. So there are two scalars, S and scalar. So originally we have a 2 inflaton system, but this can made a single inflaton system using the so-called Valley approximation. What is the Valley approximation? Yes, this is the contour of the potential in the plane of the scalar and the S. And in the Valley approximation, we assume that the inflaton slowly rolls down along the bottom line. If you assume this, then this is effectively one inflaton system. If you have a one inflaton system, you can use the conventional formula to calculate the inflationary parameters. And this is the result. So this is the result in terms of the scalar ratio and the scalar index plane. And this green, yellow lines is the predictions. And the left tips here the prediction of the R square inflation. So it approaches the R square inflation. And the upper tips correspond to the prediction of the linear potential. And this colored area is constrained by Planck and by the gap. So in certain areas, it's consistent with the expression. Now here you see I use this parameter, and the beta, which is C, is varies 10 to 100 to 1,000. And kappa is arbitrary, so we can satisfy the kappa constraint. But gamma over beta S is between 10 to 6 and 10 to 8. And as you remember, this is, of course, is conflict with the naturalness condition. The kappa is okay, but the gamma over the beta has to be larger than 10 to 14, and this is not satisfied this model. So we have to use some kind of the fine tuning to suppress the correction to the exporter coupling. Now, come to the dark matter. It turns out this fermionic dark matter can be a consistent dark matter. It has a Yukawa coupling like this, and S is one of the inflaton, and S decays into dark matter. And this is the mass of the dark matter. So yes, this is the Yukawa coupling which enters onto the mass, and inflaton decays into gammas. One can express the mass of the dark matter in terms of the reheating temperature. Of course, we have no reheating mechanism, but there is a way to constrain the reheating temperature by given a set of the inflationary parameters. So we use this equation and calculating the dark matter mass. So this is the plan. It's horizontal plane, horizontal axis is the reheating temperature, and yes. Horizontal is the dark matter, and the vertical is reheating. And this horizontal dotted line is the lower bound of the heating temperature for thermal leptogenesis to work with latent neutrino mass more than 2 times 10 to 7 G. All right. So this is a very specific model, but there you can imagine there can be many different models. For instance, we have used or replaced this Coleman Wenberg by hidden QCD, like cosmos model, and it works also, very similar prediction. But we can also include wild tensor square term. This is interesting because as you remember in the Lagrangian, we introduced sigma for the different Wenberg mechanism to work. But if you include the wild tensor squared, we do not need sigma. So we have only one extra scalar and wild tensor squared. Because the wild square tensor in the background of non-vanishing scalar, this becomes massive. This is a ghost mass. Since it is a massive, you can compute the Coleman Wenberg contribution, and this is the result. So although this is a ghost, you get plus sign here, and the form is very similar to the ordinary particle. Then you can use this, then you can break scale symmetry spontaneously, and you can have Einstein term, and you can discuss also inflation. This is the result of the inflation. It looks very similar to the prediction of the previous model, and also the beta and gamma values in a similar, a little bit different but similar. And you can also find that naturalness condition is not satisfied in this model either. Okay. So this has my talk basically, and I come to summary. So electroweak scale and dark matter and Planck scale can be spontaneously generated, as you see, both perturbatively and also non-perturbative. And in these theories, the naturalness problem of the Higgs is converted to the naturalness of the Higgs-Potter coupling. Since Higgs-Potter coupling is a dimensionless and it has only quadratic divergences, multiplicative solution for the naturalness may become possible, but this is not always. This does not always guarantee if the gravitational corrections are included, as you will see. We have also seen there is a descent. If there is no intermediate scale, there is a descent from the standard model scale all the way to the Planck scale. And if you, in addition, assume that the Planck scale is generated spontaneously, there is a direct connection between the standard model and Planck scale, as you see. And this direct relation influences the naturalness of the Higgs-Potter coupling, as you have seen, and also influences the inflationary problem. Yeah. So there are many scale invariant extensions of the square model of Stravinsky. In this model, tensor to scalar ratio is predicted very small, but usually slightly larger than prediction of the square inflation model, but contains at least more than 2 scalars, right? So if the model contains more than 2 scalars, and then is it possible to distinguish these models by measuring small tensor to scalar ratio and also non-Gaussianity in the CMB anisotropy and large scale structure by further experiments such as light bud and so on and so on. Okay, thank you very much.
Thank you very much for your interesting talk, Professor Kubo. Now open to questions and comments. Any question or comments from audience?
May I ask a question? Thank you very much for
please.
your talk.
Yeah, please. Yeah.
I try to follow as much as I can. And
Yeah.
actually, I should have asked in the middle of your talk, but there are several things spread over your talk. Let me go to the neutrino option first. Sorry.
Yeah. Yeah.
Because
neutrino
you are replacing
yes.
the
Yes.
original problem of the hierarchy,
Yes.
original hierarchy problem by this mixing quality coupling due to the loop corrections. So here, in the presence of equal coupling to the right-handed neutrino, you always have this Higgs mass correction, right?
Yeah.
So
You mean this one? This one?
Yes, the first diagram exists where you are kind of protecting this mass correction by symmetry, or
Yes. After scale invariance is broken, you have this diagram. But before the scale invariance is broken, there is no mass.
I see.
Right?
So here
there is
I
no
guess
mass.
I see. So the new particle mass, the mass of the right-handed neutrino, due to the vacuum expectation value of the single scalar.
So if you work within the effective theory, then you have mass and so on and so on. You have quadratic divergence. But in the original theory, there is no mass. There is no quadratic divergence.
Okay.
Only logarithmic divergence.
So there is no bare mass for the right-handed neutrino.
Yeah.
Okay.
And as I told you, the bare mass cannot be created.
I see. Okay. Okay, I now understand. Okay. Maybe another question. Maybe then we can go to another question from the other people.
Yeah.
You mentioned about this Ostro-Bredesky problem.
Yeah, problem. Yeah. Yes.
Then there are two interpretations of this cost problem, right? Then
yes.
Then if we want to have a positive problem, like a unitarity problem, if there is no unitarity problem, it is unavoidable to have negative energy states. That's what you wanted to say.
What I wanted to say is, if you choose, do you see my screen?
Yes.
Okay. Conventional definition, you have negative norm, right? But with positive energy. And if you use the other option, then you have no negative norm. So this is, you can have a positive, you can define the probability, amplitude, probability. However, you have negative energy. What happens if you use this quantization to the case that I showed you, right? To scattering and so on. Then there will be a probability. So let's go back to this scattering. Scattering, this is a classical scattering, but you can imagine, you can discuss the scattering at the quantum level, right? So at the quantum level, you can have something like this. You have incoming particle, and the ghost oscillator is excited, right?
Yes.
But since we have a quantum mechanism, there is a probability that the ghost can be excited with large energy. Okay, there is a fast excitation, second excitation, and so on. So there is a tiny probability that the ghost is excited at large, let's say negative large energy, because all the energies are negative, which means since the energy is conserved, that the outgoing particle can have infinite large energy. There is a probability, tiny probability, that the outgoing particle has infinite energy, or almost infinite energy. This is very strange. And this quantization corresponds to this one. The
I see.
other one, you have a positive energy. It does not happen like this. However, I cannot have a probability interpretation because of this negative. But you can imagine, since in the quantum mechanic, there is an energy gap, because to generate the harmonic oscillator to the first excitation, you need the energy, right?
Yes.
So if the incoming particle energy of the incoming particle is small, then this incoming particle cannot excite the harmonic oscillator. It's not analytically enough.
Right.
So in this case, because the harmonic oscillator is not excited, it remains under the ground state basically. After the scattering, you can have probability interpretation in this case. Okay, probability to calculate the probability, you can sandwich the state, right? Incoming state and outgoing sandwich. You do not sandwich the between. They are virtually, of course, excited, but the virtual excitation does not count for the probability. Only the incoming or in state and out state. And for the harmonic oscillator, if the incoming energy is less, incoming and outgoing the same. This is the ground state, both. So ground state, probability that the ground state remains ground state. This is a sandwich between ground state. They have positive norm. So in this case, there is an exception that the probability interpretation can be made. For instance, but in the quantum field theory, the situation is much more complicated. Not only this, in the maybe if you have in the quantum case, quantum field theory case, there is an old problem. There is a model called Lee-Wick model. Maybe Kosan know this old model. Yeah. Lee-Wick model. The situation is very similar. And what Lee-Wick found is, in quantum field theory, that these ghost particles, yes, say they make a pair. At the classical level, at the Lagrangian level, at the tree level, there's no ghost particle. That's like harmonic oscillator. But at the if you include the quantum corrections, they become the so-called pair of complex ghosts. Complex ghosts mean one ghost has a complex mass. So you have a pair of ghosts with, let's say, M is a complex, and there's a particle with M, and the other particle with M star. So this situation, of course, does not appear in the quantum mechanical situation, but this appears in the quantum field theory, which makes the problem much complicated. How to deal with this complex ghost pair? And there are of course many suggestions how to deal with this. I wrote this, differences, for instance. You can look at these papers. Yes.
Yeah.
They have different, idea to solve this problem. Even it appears also in the 70s. Okay? Coleman wrote a review paper about this after the Wick proposed this model. This is much before the spin-to-ghost problem.
Okay, thank you. Maybe I have more questions, but feel free to ask.
Can I ask one question?
Yeah, of course.
Yeah, thank you very much for a nice talk. So in the near the end of your talk, you gave some predictions on NSR, etc. And here, do you assume what do you assume for Weil scale term? As I was wondering what did you do with this spin ghost? Is it irrelevant or?
No. Here, for the first model here, I showed you. Here, I assume that the Weil scale term is absent.
Okay.
For this model. However, here this model, this Weil scale model is present. Yes.
then that Wildskier term is the source of this spin to ghost term in quantum physics, right?
Yes, it is. There is in this model there is a spin to ghost.
So how did you deal with that? Or
The spin to ghost is a yes, but it does not appear in the inflation. Inflation is basically the classical problem. Yes.
okay.
So we ignore this unitarity problem in this case. But even if you assume there is no wild square term at the beginning, right? But if you include the quantum corrections, this term always appears.
Yeah, right.
Right. So if you go to quantum corrections, this term is always there.
Yeah.
So this is If there is a way to suppress this term, then this would be very nice. But this term is always there. So therefore, this problem is really a very serious problem.
Okay, thank you very much.
On the other hand, it is a renormalizable theory. And so it will be very nice if we could solve this problem. So if you could solve this problem, this is one of the quantum gravity, consistent gravity, quantum gravity.
Any other question? Sorry.
No, sorry.
Please, yeah.
Sorry. Any other questions? If no, so although this is a ghost, please.
Can I?
Yes.
Or is someone going?
Okay, no, please.
I'm sorry if someone was going. I will
In the
wait.
last slide, you mentioned about non-Gaussianity to distinguish to model with sigma and without the sigma field. Could you explain more on this? You mean the sigma field affect the impression or something? Yeah, I remember in the impression analysis, you solved the two-field system, but they are from S field and scalar, right? And then, I wonder the role of sigma, and maybe it's important to distinguish this model, right?
Yes, here I assume that the sigma does not play any role for inflation, which means the sigma remains basically zero, right? Of course, this is an assumption. If you assume this, sigma does not play any role for inflation, so sigma remains zero during the inflation, then I have only S and scalar. Of course, sigma can contribute, of course. For instance, it may be possible that the sigma acts as curvature, for instance. If it is a curvature, it does contribute to non-Gaussianity. But even without sigma, S and the scalar, this is a two inflaton system. It does contribute to the non-Gaussianity. And there are some papers also, not explicitly in this model, but there are many models with one scalar and one scalar, and there are papers in which non-Gaussianity has been computed.
And also the spin to ghost can affect such non-Gaussianity or?
Yes, in this model, I have only one scalar and scalar. Very similar to this model. If you assume the sigma does not play any role, then maybe we have similar non-Gaussianity. But I don't know. We have not computed yet.
And also for the discussion of ghost, I briefly read the paper on the recent development of the ghost problems. And if I remember correctly, they discussed the self-energy of the ghost particle. They consider the system with, how to say, the ghost particle plus some matter system, and they study the quantum correction and the ghost propagator. And then, if I remember correctly, the imaginary part of the self energy actually the sign of the self-energy is important to solve the unitarity issue. And so yeah, it's related to this slide. You mentioned we have a wrong sign for the propagator, but you say the sign of the I epsilon is also important, right? And I think the second sign flip is also related to the self-energy. Is it correct, or maybe I forgot some important stuff, but yeah.
Yes. What you said is related to what I said, Liebig, right? Let's start with Liebig. They have computed one loop correction, right? And they found the position of the pole. If in the usual quantum field theory, if you look at the one loop, for instance, Z propagate of the Z, and the fermions are propagating, it will generate a decay constant, right? You produce an imaginary part. Imaginary part is the decay constant. Now, you can compute the same thing. And Lee and Wick, as I told you, they found something completely different to the usual case. Namely, I told you, they found at the quantum level, you can have complex pairs of the ghosts. Okay? This is the original finding of Lee and Wick. So you can compute a very similar thing in the quantum gravity, which is done, for instance, this paper, Dolphin. They have computed all these things, and they found an imaginary part, and they interpret this imaginary part as the decay constant of spin 2 ghost. So in their interpretation, spin 2 ghost decays, right? Decays in matter. And they found that, change of the sign and the change of, actually this sign changes if you include quantum corrections, and this sign of the change indicate the consistency of the unitarity. This is the interpretation. However, original Leon Wick and also Coleman said that these ghosts are stable. Why stable? Roughly saying because their mass is imaginary. So if imaginary mass cannot decay into particles with real masses because of energy conservation. Energy conservation said imaginary part as well as the real part has to conserve. So in this case, the complex ghosts cannot decay, for instance, right? So this is, for instance, discussed also Anzalmi. They have, as I understand, they have stable complex ghosts. So this, as I told you, this problem is very complex, and the interpretation and how to treat them is quite different. And
Okay,
therefore,
so
I told you that, yeah.
There's still a kind of a controversy or contradiction between the discussion.
I would like, yes, I think the problem is not solved yet. Yeah. Okay. And we are tending to think that the ghost is stable, in contrast to this paper. They discuss the ghost is unstable. The discussions like this, in the usual case, if you have an unstable particle like Z, for instance, Z is unstable, this unstable particle do not appear as asymptotic state, right? They are not asymptotic state. Asymptotic states, they are only stable particles. If the particles decay, they are not asymptotic. So if there is no asymptotic state, ghost state, and if there is no ghost in the asymptotic state, you have only positive norm, right? And in the usual case, this is somehow proven by Weltman in very long time ago, that unitarity. So if you exclude the unstable particle from the asymptotic state, unitarity is still there. So unstable states do not contribute to the unitarity. if this is true for the ghost too, then maybe unitary. Okay? If you can prove that the unstable ghosts do not contribute to unitarity, then the unitarity is there. But this is not so obvious.
I see.
But,
So
but with yes.
Yeah, please, sir.
I think they consider I think the unstable particle maybe then some decayed particle running in the loop and then cut the self energy to show the unitarity. So I think that there's some assumption behind the for self energy.
Yes,
Do you remember the correct statement about the self energy correction? Because they have a ghost particle coupled to extra particle, right? Then this try to let ghost particle to decay into extra particles.
The point is the following, right? If I don't know if you have so much time now. If you compute the one loop correction, let's say for the Z boson, okay? One loop correction, then it produces imaginary part, right? In the propagator, okay? This imaginary part, right? This imaginary part contributes, or the imaginary part is there, not for the physical. So if you go to the complex plane, not the first seat, in the second seat it appears. So if you have a complex DR ax and go around the complex plane, there is no pole. The pole appears on the second seat. If you look at the field theory, once again, you will see that. Not under the first seat. Yeah? On the second seat. This is a conventional case. However, if you do this same computation for the ghost, it appears on the first seat. First seat means this is the, let's say, p square on the first seat means basically we call it the physical seat. Okay? And the pole appears on the physical seat. So this is the really pole. In the conventional case, it's not the really, it is not the pole on the first seat of the complex plane.
Okay.
Since it appears on the first seat in the ghost case, it is a really pole of the propagator. So this is the difference.
Yeah. So
if it is a really, since it is a really the pole, it is not a decay constant. It is a complex mass. This is the interpretation of the original interpretation. So we think it cannot be, it should not be interpreted as a decay constant.
I see.
It should be interpreted as a complex mass.
I see.
Since it is a complex mass, it should be stable. So, but still, this discussion is going on.
I see. Yeah, right? So there's some related discussion about some inverse time ordering because of you want to avoid this extra pole in the first sheet.
Yeah.
Instead, and rig rotation could be different, could be done differently. Instead of plus 90, you could do minus 90-degree rotation in order to avoid that pole. Then the propagator definition changes. So it's different. It's not going from minus infinity to plus infinity. It's coming from plus infinity to minus infinity. So it's totally it's not understandable at the point. So
yes. Anzalmi is proposing, such kind of very complicated calculation of momenta. And I'm still studying his paper, but it's very complicated.
Yeah. Okay.
And he said he have solved this problem. Right?
Okay, thank you for your pointing out this old discussion. I think it's worthwhile to look at these old papers. Okay, maybe since the time is running out, but I think that we should take more questions. Kimiko, take more questions.
Yeah, I think, Carlo, do you have a question? I thought that you have a question.
Yeah, if possible, yes.
Yeah, we still have 8 minutes about yeah. So
But thank you. First of all, thank you for the talk, for this time. And well, basically, I want to come back to the fact that you were talking about possibly having a pattern towards a solution for the naturalness hierarchy problem, and I actually don't see how you really can manage to keep the quantum corrections small, and in particular how you can keep the breaking of the classical scale invariance as just a spontaneous one. I try to be more explicit. If we take, for example, the Coleman and Weinberg in their original paper, Coleman and Weinberg acknowledge a quadratic divergence, they cancel it, and then they obtain the result that you showed us, and that especially brings the minimum such that the mass would be 10 GeV and is inapplicable for phenomenological interests. But they acknowledge this kind of divergence. Now, even if you do not start with a classical Lagrangian was a mass, the quantum correction will bring you this lambda square term, and I don't see how you cancel it. Even, for example, the neutrino contribution that you showed us the neutrino mass squared correction, which of course is not present in the case where you start with a zero neutrino mass, but there still is the coupling times the lambda square, which you did not acknowledge. So I want to know where this is, and if you're canceling it.
Okay, there are two problems. First of all, there is no, if your theory is scale invariant and renormalizable, there is no lambda square contribution. You could obtain the lambda square correction if you, for instance, use let's say cutoff regularization. Yes, the cutoff regularization breaks scale invariance. Therefore, if you produce a lambda square, but this has no physical meaning. So in the scale invariant theory, as I told you at the very beginning, what you're saying, the anomaly, okay? Anomaly comes because we have to regularize. It's very basically the same. Scale invariance is broken by anomaly, but scale invariance does not produce the mass gap, and lambda square is not a mass gap. You have to produce also the Coleman Wenberg. This is due to the anomaly. Okay, this quantum correction comes from the anomaly, but it does not directly generate a mass gap. For instance, this is a good example. For instance, if your top mass is heavy, right? There's a quantum correction because there's an anomaly, but it does not generate the mass gap. So in the scale invariant theory, the quantum correction does not generate a mass gap. This is the first thing. So the second thing, it depends whether you work within the effective field theory with masses, where the scale invariance is broken, or you work in the original theory, which is scale invariant from the beginning. So you can compute, in principle, all corrections in the original theory, not in the effective theory. In the original theory, since there is no mass parameters and renormalizable, there is no correction to the mass parameters, no correction. You should compute in the original theory. Original theory, there is no mass parameter. There is no correction to the mass.
I know I've been in contact with people working in these or similar field. So I know the argument that that is usually brought against, for example, a cutoff regularization for this type of theories. But at some point, it seems to me that then you are putting by hand at first the idea that there should be no mass scale, no lambda dependence, and I believe you are using, I don't know, either as the scale invariant regularization proposed by Shaposhnikov and then Gilencia some years later to calculate the quantum corrections, or some other technical schemes. But I don't see how you can say by at first that there is no physicality in the art cutoff
There's no
regularization. Otherwise, you are taking
you can use of course also regularization that breaks scale invariance. Okay, so you produce a lambda square, right? You subtract just it. That's it. You can subtract it. There's no problem. The physics should not depend on the regularization.
Yes, of course.
You can compute also, or you can also compute the Coleman Wenberg using the cutoff. You produce the mass term correction, but you subtract just it. You get the same answer.
Yes, but indeed, Coleman Wenberg
It has nothing to do with the it has nothing to do with the hierarchy problem. If you have a mass term, yes, from the beginning there is a contribution, quadratic contribution to the mass term. But you do not have, for instance, if you compute, for instance, Coleman Wenberg using the cutoff, for instance, you do produce the mass term, but the divergence cannot be absorbed. Right? There is no mass term from the beginning. In that case, you have just abstract. Since, for instance, you can compute also the quantum corrections in QED using the cutoff, there's no problem. You get the photon mass term, right? Because you break gauge invariance. But you just subtract it. And afterward, after you have used this scale invariance breaking regularization, after you have computed, you have to correct through the finite corrections so that the whole theory is gauge invariant. And after that, the photon mass is absent.
I see, I know the point, but
Do you see that do you see that the gauge invariance is broken?
Yes,
gauge invariance is broken because if you use the cutoff.
Yes, but gauge invariance is even a different type of invariance. We call it the same way, but it really means another thing.
Gauge invariance is not broken by regularization. Gauge invariance is broken only by anomalies, say.
Yes.
You cannot break the gauge invariance by regularization.
Okay,
Yes,
so
if regularization break the gauge invariance, you have to correct it after that. If you cannot correct by any meaning, then it is anomaly. But as I said, scale anomaly does not produce the mass term directly.
And so just to
this
finish,
is misunderstood many times. Scale invariance, scale anomaly does not generate the mass term directly, mass gap.
Yes, and just to finish at the end, it truly means that you are saying at the start that your model is quantum mechanically scale invariant and not just classical scale invariant.
No. Not quantum mechanically, only classically scale invariant. Quantum mechanically, I break scale, of course, by anomaly.
But you are saying that whatever is a hard breaking of this scale invariance is something that I should cancel. If I proceed in ways, no.
In fact, anomaly is hard breaking, but I'm not saying that any hard breaking. Hard breaking by anomaly does not produce the mass term or the mass correction, right?
Okay, I see your point.
Yeah. This is many times misunderstood, especially in the society of supersymmetry.
yeah, basically bare mass term is cancelled, kind of assumed to be cancelled, right? So yeah. So maybe do you have any?
I only have one small question. Yeah, sorry. It's already time, so sorry. I have a small question. I remember you introduced a real scalar field S. I'm just wondering why linear term of the scalar field S times the rich scalar is absent in your Lagrangian. Just I'm wondering.
That should be not scale invariant.
I see. This was not scale.
Right? Yeah,
Yeah, right.
S has dimension 1, and so if you have a linear term here, then you need a dimensionful parameter.
Ah,
Dimensionful
yes.
parameter means
Yeah, right.
you break scale invariance.
Ah, yeah,
Right?
thank you very much.
Okay.
Yeah, thank you very much.
Actually, so we are so obliged, so obsessed by this ghost problem. I need to ask this quick question about this kappa parameter. You mentioned the effect of kappa by square term on the tensor to scalar ratio, and in the previous work, and you did Coleman Wenberg correction. Can you comment on that, on the difference between the two approaches?
I hope I understand the question. First of all, the kappa contribute to the predominant perturbations, right? As you have included in your paper, okay? To the tensor to scalar ratio. This is not what I mean. What I mean is that if you look at the mass of the ghost, looks like this, okay? In the background of the S. And then you can integrate out the fluctuation of the spin 2 part. Like an fluctuation of the spin 1, it's a similar computation. Then you get this Coleman Wenberg potential. Then you can use this Coleman Wenberg potential to break scale invariance.
So in this previous work, the Baumann et al., what did they do? So what did they do with this bi-square term?
They have computed the tensor perturbation, contribution to the tensor perturbation in predominant, right? Has nothing to do with the Coleman Wenberg. This is completely different, right? They have calculated the contribution to the tensor to scalar ratio, right? And we have computed the potential. This is two different.
I see. They did
computed
some
potential. Yes.
I see, perturbation, kind of perturbation analysis.
Yeah, but not the potential, right?
Not potential, I see.
So basically, gravitational wave contribution to the the model perturbation.
So in your case, this Coleman Wenberg potential is the only source for spontaneous symmetry breaking, or
no, we have both.
You have
S should be there. S should be there, right?
S is I mean the couplings.
Yes.
There are other couplings in your model.
In our model, we have, let's see, yes, all the terms are there, except sigma is absent. Sigma is absent, and these terms are there.
I see.
Right?
Just I wanted to know how does prediction change if you include Coleman Wenberg contribution? If you don't have a Coleman Wenberg contribution from spin 2.
Yes, we do have a Coleman Wenberg from spin 2, this, right? And this is the prediction is very similar to this model. Very similar.
So previous model, they are almost the same, but the coupling,
of course,
are different.
Couplings are different because this coupling is absent, and also the range of the betas and the kappas. There's no kappa here, but the beta and gamma is slightly different. But prediction itself is very similar.
I see.
You know, the right tips are basically R square inflation, and here is the linear inflation. And this form is very similar. Yes.
I see. Okay, thank you.
Yeah.
Almost time is a bit over. Professor Pyongyang-ko, do you have a question? Professor Pyongyang-ko, I thought you have a question.
No.
Okay, I just misunderstood. If there are no more questions, then we should probably close this question and answer time. So let's thank Professor Kubo again.
Okay.